correction when the width is finite. In fact, here is the plot. This blue plot is when the width is finite in a definite CFT. It's actually the minimal model CFT. When the width is finite, the profile is of this kind. And what we will do is basically evaluate the epsilon squared correction, the width squared correction to it. And we will show that the width squared correction is universal. And it sort of corrects this bump, this step function bump of this kind to this particular feature, this red feature. Okay. So this is what I've explained. Epsilon is equal to 0. The dashed line was actually found by these authors. And this jump is also related to the operator. It's called this quantum dimension. It's related to the characteristics of the operator. We'll come to it. And the general shape of the curve, of course, the way it sort of smoothens out depends on the details of the CFT. But this growth is independent, and in fact it is independent of central charge even, and we will show that it's universal. Okay, so that's the sort of rough result. So the details. So how do you set up this question? Is basically first you write down the density matrix. Here's the density matrix. So this one is basically the thermal density matrix, and here is the operator insertion, which creates the particular state. The state is smeared over epsilon by this particular Hamiltonian. In fact, by imaginary evolution, the state is smeared, and then it's evolved in time t. Okay. So, in fact, this evolution can be thought of as insertion of the operator at complex times like this, and then it's evolved. And the coordinates we will discuss are basically in Lorentzian signature, light cone signatures of this kind. For instance, so let's see if this density matrix corresponds to the state we are interested in, basically this pulse traveling on the light cone. So what you do to check that is basically evaluate the stress tensor in that particular density matrix. Here it is. And in fact, you can translate it from this particular definition to a correlator. In fact, it's the 3-point function of the stress tensor inserted at x minus t and x plus t. You can see how the insertion operator acquires the the evolution time dependency which I evolved here. And this is the normalization basically. Okay, and this is an easy correlator to evaluate. In fact, it's a stress tensor with two primaries, and you can evaluate it, and you can see this is the formula. Okay, and in fact, you have to translate it to the cylinder. And if you plot this, particular function, you can see some kind of Lorentzian kind of structure here. So if you plot this particular function, you'll see that at t is equal to 0, it's a bump. And then it splits, the bump splits, and it travels on the light cone. You can actually see it in 3D if you want to see, but here I plotted at 0.05, and you see it's at 0.05. And so this pulse travels, and it moves into the entangling interval, and we are asking the question, how does it change the entanglement entropy? Yes? Yeah, the line is infinite, yes. No, it's not a torus. This is an infinite line. But at finite temperature, so it's cylinder. So, to evaluate entanglement entropy, so we use, of course, the replica trick for the reduced density matrix, and in path integral basically translates to path integral of the cylinder with a branch cut at these points, at the points of the interval, and there is the insertion of the operator at these imaginary times. Here is the particular sort of structure of the branch cut cylinder. Here's the beta and the insertions of the operator, and I have not drawn it well, but this is the branch cut x2 to x3, and these are the light cone coordinates of that, x2 and x3, and of course these sheets are joined together at the branch cut over and over again n times. Okay. So at every sheet, there is this insertion of these operators. Okay. Okay, so basically on the n-fold cover of the cylinder, this evaluation of the trace of the density matrix translates to evaluation of the two endpoint function on this branched cylinder. Okay. So we'll have to evaluate the two endpoint correlator on the branched cylinder. Now, of course, that seems to be a hard task. Okay. So again, I have detailed sort of setup. So there are these operators insertions, and at every copy of the cylinder, there are these O and O dagger insertions, and the branch points are located at this points. So they're separated by distance, spatial distance L1, L2 minus L1. Now, the Rene entropy is basically given by the change in the Rene entropy is basically given by the insertion, the density matrix with the insertions, two-way insertions, divided by the usual density matrix on the branch cylinder. Now, to evaluate this two-endpoint function, you go to the covering space. You go to this. You use this uniformization map, which takes this branch cylinder to a plane in which each copy of the branch cylinder is basically a wedge of 2 pi by n. Okay, width 2 pi by n. So here's the map. Here's the map. It's sort of, you can understand it if you stare at it for a while. Basically, it takes the cylinder to this wedge. This 1 by n takes into account for that. And if you look at if you track the insertions of the operator in time, okay, this is how it behaves. So it's sort of so you can see here are the insertions of the operator here. It's on a wedge, okay, and here are these insertions, okay. So this is like I epsilon and minus I epsilon, and so on, repeated onwards. The key point to understand is that as when the time changes, actually, this insertion changes in a particular way, and what happens is that when the time is such that it enters the interval, then this W1, which is very close to W4, they were 2I epsilon separated, they sort of, the W1 approaches W4 in the adjacent copy. So let me emphasize that again. So basically the key point is that when the time enters this interval L1 to L2, the operators approach the adjacent wedges, and this is only in the holomorphic side actually. So the way to see it is the following: evaluate the particular cross ratio. And you see, and the epsilon is going to 0, epsilon was the width, and you see that there is a change in sign when t is between L1 and L2. And because of the change in sign, okay, this flips, and therefore, the nth roots basically pick up a phase 2 pi by n, and that sort of rotates the holomorphic side such that it moves close. W1 moves close to the adjacent branch. Okay. Well, the anti-holomorphic thing remains the same. There is no change in sign in that, and the anti-holomorphic coordinates remain the same. So this is a key point to realize that. So maybe I can sort of mention it in an n equals 2 setup. So here is W1, W4, and here's the copy, W1 and W4, copy. And initially it was like this together, and then after the time, in between time L2 to L1, this thing appears closer. So there is sort of a flip in that. So here again I have written that this thing, what's the phenomena. And the next step is, because epsilon is approaching very close, you can actually evaluate the two endpoint function by using the operator product expansion of this O and O dagger. And say we assume that conformal dimensions of the theory of the lowest lying conformal dimensions primary are greater than 1. Just assume that. And then what is important is basically the stress tensor which appears in the OPE. Okay. And if you want to approximate this two endpoint function by its OPE, then all we have to do is basically evaluate the expectation value of the stress tensor on the branch cylinder. Okay. So this two-end point function, each of them we take epsilon close by, and we have to evaluate the expectation value, and then so all you have to do is basically expectation value of the cylinder, of the stress tensor on the cylinder, branch cylinder, and that also can be done using the uniformization map. So what happens is that because of this flip here, the flip in the holomorphic side, at every time it flips, we have to use this fusion transformations. When we sort of flip the branches, we have to use the fusion transformation and let the fusion transformation be FOO. And putting all this together, we can approximate basically the two-end point function. The two-end point function essentially admits this particular expansion. Okay, and the epsilon is equal to 0 term is basically the step function. And the step function, this happens because, as I said, when the branch flips, there is a fusion coefficient, and basically you'll have to take the log of that. And the epsilon squared term, we evaluate by evaluating the expectation value of the stress tensor of the branch cylinder, and that leads to this. And essentially this coefficient, this term which appears as epsilon squared term, is basically a Schwartzian which takes you from the branch cylinder to the uniformized plane. So that's it. Okay. And that has this very universal time dependence. And in fact, what appears here is just the coefficient of the dimension of the primary. It doesn't even have the center charge, and this whole thing is a universal time dependence. So let's write the result in a more general way. So here it is. This is the epsilon squared coefficient, and all you have to do is evaluate the expectation value of the stress tensor on the branched cylinder geometry. The branches are at these points, okay, and substitute that, and then you will basically get the time dependence. Okay. And as you can see that from this evaluation, this object is this time dependence is entirely universal. It just depends on the map, and also it's important to realize that this expansion, epsilon expansion, is an expansion when the times are not very close to the limit. So let's see this in slightly. Let's have another more intuition about this term, and it also will lead to certain checks. Okay. So if the time, if first we take what are the intervals to be infinite. We take the intervals to be infinite size, and then we take large times. Then you see that okay, you basically ignore the initial region. Okay, and it's basically a branched cylinder. Okay, it's just a cylinder branched n times. So its expectation value, it's just a cylinder with n beta periodicity. Okay, and it's basically so it's a stress tensor expectation value on n beta periodicity, and then you can evaluate it. This is the expectational stress tensor on the cylinder, and then again we can take this asymptotically static jump in the entanglement entropy of this kind. So this, of course, can be reproduced exactly from the time-dependent profile too. But there is an intuition to see how this becomes static and so on. So there is sort of gives an alternative check. So let's see the checks we have done for this profile. So we have checked this analysis, this OPE analysis, which I mentioned, against a 4-point function correlator, in which we evaluate the 4-point function using conformal blocks. Okay? So at epsilon squared. Then we compare it against minimal model CFT. So in a minimal model CFT, especially in the second Rene entropy, so this is a minimal model CFT, PP prime minimal model CFT. This is the central charge, and here's the primary which we'll focus on. And the 4-point function of these primaries are known. If you're looking at second Rene entropy, it's just a 4-point function, and the 4-point functions of these operators are known in terms of hypergeometric functions. And of course, so it's an exact result in epsilon. Okay, and you can evaluate epsilon squared and compare it against the OPE analysis, and of course it agrees. This is the quantum dimension, and here is the epsilon squared correction. And here we have plotted again. This is the quantum dimension jump, and here is the epsilon squared correction to it, okay, which gives you this profile of growth, and this is the exact result for the second run entropy in the minimal model. So this is the comparison. Again, I have zoomed in on this particular aspect. Yes. Then there's a correction for an, there is a, I have chosen the PP prime such that the one is above. In fact, the next thing I said is that we have repeated it for the free fermion model, in which there is a U1 current which contributes to the epsilon square. And of course, if you subtract that U1 contribution, you will get this answer. So that is a check. So let's go over to the higher spin deformed version of this calculation. So this is for any 2D CFT. So in higher spin deformed version, so we consider the CFT with higher spin S chemical potential, and it's deformed in this particular holomorphic manner. Okay. And this deformation is introduced in each copy, this deformation of the CFT. So it's in the calculations of Brenner entropy. So this deformation is introduced in each copy. Okay. And so here is the deformation in each of these copy. And what we have to do is basically calculate. Now the question is that, okay, we want to correct our calculation to say some mu squared order, but eventually corrected. So we'll have to calculate these correlators along with this deformation. So for sufficiently small mu, in fact, this is just the scaling analysis. For every order in epsilon, there is a mu expansion, and then one can correct this, and there is this order epsilon squared, mu squared correction, and this is the leading term. Actually, we can show that this is the leading term, and we can even show that this is universal. So that's the next sort of calculation. So the time dependence, just like exactly, you got to argue exactly the same way. So we have these operators close by, okay, O and O dagger close by, and now the CFT is deformed with higher spin chemical potential, and therefore perturbative analysis, conformal perturbation theory says that you got to bring, I mean, from the action, you got to bring down sort of these additive terms in W, and the correction basically turns out. When you use the OPE, it turns out that you have to evaluate the following correlator: stress tensor and W and W. So this is the first insertion actually vanishes from just the TW correlator. So it's only the second insertion, second time of second order perturbation theory which contributes at order mu squared. And of course, because it's a conformal perturbation theory, you have to integrate this, integrate the current over the cylinder. So this is the thing. So as seen from here itself, you can see that this is a correlator of currents, and therefore, since it's a correlator of currents, it's universal. Okay, and there's a correlator of currents on the branch cylinder, and you know, you have to do that integral, but the integrand is universal, therefore the integral also will be universal. And what we did was, earlier on, various works, we developed the prescriptions for doing these integrals. And these prescriptions, there is a definite prescription, or sort of ordering prescription for evaluating these integrals, and that was checked against various methods. It was checked against holography, in which we corrected the entanglement entropy. You know, we compared it against entanglement entropy of Wilson line. So it was checked against holography. It was also checked for the free energy against alternative perturbative methods developed by these authors and Matthias here. So the prescription sort of works. Okay, so we use that prescription. I mean, there are checks for that to evaluate those integrals, and they're long. I mean, the integrals are long, and let me just write the formal expression for the epsilon squared mu squared correction, which is universal. Okay, it's basically this term, and you'll have to do this integrals. And I wouldn't show you the expression for the for that integral. It's in the paper, but let me plot it Okay, so we have evaluated the